But let's do the dimensional derivative. So we'd have something like for q dot, and then it would be equal to 1 over Iy, because we always normalize by the moment of inertia by the mass. So partial m over partial q, and we have to evaluate that, of course, at the steady state condition, and then that would be times delta q, or times q. And then there would be the rest of the terms. You know, we look at these as motion variables, all the rest of it. But this one here is what we have called the stability derivative. The stability derivative is this guy right here. And we can see it's going to have dimensions, radians per second squared. So if I get radians per second over here, then that means that this dimensional derivative has to be 1 over seconds. So that radians per second squared comes out left and right for all the terms. So that's a dimensional derivative, and we call it mq, as units of 1 over second, like so. And in the table, I'll look up CMQ, right? I'll look that up in the table. So how do I get MQ from CMQ? You have to know how to do this for all the stability derivatives. You have to know the name, and you have to know the physical description. So the name of this is pitch damping. And why would it be called pitch damping? Because whenever I have a pitch moment, or a pitching rate, a Q, whenever I have a Q, you see how the tail is wagging in the breeze back there? So the longer the tail, the more it would be wagging, right? So it's generating an angle of attack that's opposing the motion. Whenever I go like this, it's generating an angle of attack that wants to counter that motion. Otherwise, it would spin out of control. So the pitch damping derivative is always negative, and whenever I have a positive Q, again, if I stick my right hand down the right wing, this is positive Q, I want a negative moment. So my pitch damping moment is negative. So that kind of summarizes what I expect you to know from all these stability derivatives. This is pitch damping. The sign is negative for stability, right? And physics says that it will be negative whenever I have a positive Q. The moment from the tail moving, or the Q from the tail, is going to be negative. And you can convince yourself that's the case, even if I move even if it was a canard, you can convince yourself that would still be the case. There would always be an opposing moment. So, this is pitch damping. It's going to be equal to 1 over Iy times the partial of the moment. Now I know the moment is Q bar SC C sub m. If I non-dimensionalize it, over partial Q evaluated at the one condition. So Q bar is 1/2 rho v squared. That's the wing area. C or C bar is the wing chord, and that's your dimensionless constant for the coefficient of moment. So this takes all the dimensions out of it: pounds per square feet, foot pounds. I got foot pounds here, so there's no moment on this. Foot pounds divided by I sub y. If I were to do this guy, this would be, I'm going to take out the SC, so we'll have, but I'm going to have units on that, yeah? Because Q has units of radians per second. So that's not allowed. So I have to have partial CM over partial Q hat. Well, Q hat's going to be dimensionless. Then I have to take partial Q hat over partial Q to give me, by the chain rule, that gives me back what I had before. I just need to know what Q hat is. Well, you can kind of guess by now. Q hat is going to be equal to wing chord Q. And there you have it. Okay. What's the secret handshake? The secret handshake is that CMQ is really CM Q hat. There's no dimensions on it. So you have to remember the secret handshake is I non-dimensionalized this, and I made all these terms appear. And there's a table in Nelson that you can maybe print out, put in your notes for the next test or for the final exam. And it's got all these formulas in it in one table. So what I'd like you to do this week, how about drag? You do drag. Drag due to velocity, du. You do du. I'll get you started. So that's going to be 1 over the mass times partial drag over partial u evaluated at steady state condition. I'll get you started. Just for your readiness check, that's going to be worth 10 points. Okay. Let's discuss this linearization example. Up here, the equation I've got has a cosine in it. And the first thing you look for when you're linearizing something, the first thing you need to do is to find a solution point. So if you have a y1, that's one means it's a solution to this equation, an equilibrium solution. If you plug in pi over 4, then this equation will work. So we're going to linearize about that solution. Well, if y1 is 45 degrees, then I've got some cool relationships that flow right out. The cosine and the sine are equal to 1 over radical 2, or square root of 2 over 2. So I draw that little picture just to get going. And then here's the second key step after you pick the equilibrium point is to have an equilibrium condition plus a perturbation about it. So sometimes this is called small perturbation theory. It's called that. So this is the perturbation. And Nelson keeps the delta for a while, which is kind of good the first time you're seeing it, because he does separate in his book the perturbation from the... So you just perturb your variable and you stick it back in your equation. And then you can see that when I take the second derivative then of the y1, that's an equilibrium, it's going to be 0. Right? And the derivative of y1 is going to be 0 because y1 is a constant. So the only term I'm going to have trouble with is this cosine, because the cosine for a small perturbation has to be mapped out with a trig identity. Okay. So here's the third thing then you have to remember. Since this is a small perturbation, what can I replace the cosine of a small angle with? Cosine of a small angle I can replace with 1, right? Because you're at the peak of the arc of the cosine curve. And what can I replace the sine of a small angle with? The sine of a small angle can be replaced with not 0, the angle itself, yeah, in radians. So that gets rid of my nonlinearity, you see, because the cosine of y1 and the sine of y1, they're constants. They're constants that come from my equilibrium solution. So if I substitute the square root of 2 over 2 for the cosine of y1 and for the sine of y1 from this equation, then cosine delta y becomes 1, yeah, and the sine of delta y becomes delta y, and I eliminate my nonlinearity of cosine delta y. So once you've substituted the nonlinearity in, you'll get a nice linear differential equation which describes the perturbation about the equilibrium solution. And we see we have a nice, so now we might want to drop the del's again if you want to drop them. And now we can go through our procedure that we should have learned in 320, right? LPT, PFE, ILT, BOT. So we take the Laplace transform, s squared plus 2s plus 2, and that gives us second order system, s squared plus 2 zeta omega n s plus omega n squared. And from here, I would expect you to be able to solve it by sight. You should be able to solve that equation. Minus 1/2 of this is the real part of my root. So I'm going to go, this is going to be minus 1, right? That's going to be minus 1 going from the origin of j omega out to my root. So I can immediately put my roots in there for the equation. From this, you should be able to write the impulse response by sight. Okay? So here's what you want to put in your pocket, write it down somewhere. The impulse response, y of t, from the impulse, is equal to twice the residue of that pole, P1, twice the residue of the pole, e to the sigma t, or minus zeta omega n, e to the sigma t times the cosine of omega d t minus the angle of the residue of that first pole. This formula always works. As I told you before, I am not going to derive this formula. I will not derive it. It is in your notes. I will begin to go over it with you and show you why it's true. But whenever I want the impulse response for any pole anywhere, I just apply this formula and the impulse response falls right out. All you have to do is remember what's that residue. How do I get the residue of this pole, which determines the magnitude of the cosine function and the phase angle? And I get the residue by drawing phasors from the zeros, putting them in the numerator, and drawing phasors from the poles and throwing them in the denominator. So, what's the angle for this, for J? What's the angle for J? The angle for J. The angle for J. 90 degrees. It's in the denominator, therefore it's minus 90, yeah? It's minus 90. So this turns out to be equal to, omega d is equal to 1, right? Omega d is equal to 1. So omega d equals 1. So this turns out to be 1/2 at an angle of minus 90 degrees. Now I went real slow again. I know I might probably have to do it again, right?